All right. 2.5, further applications of right triangles. This is obviously, it's the last section in chapter 2, but it's also the last section that we're going to cover before taking your first test. So let's get to it. So one of the things that we're going to talk about in this section is bearing. Okay, so the bearing of an object is the direction of motion in which the object is traveling. The bearing of an object is usually given by starting with a north-south line and then using an acute angle to show the direction east or west from this line. There are some exceptions to this, which I'll kind of briefly mention here in a second, but let's just practice drawing a picture of the following bearings. So let's do north 42 degrees east. So north 42 degrees east. What that means is we start with the north-south line, and remember, you know, the cardinal directions. Never eat, I always remember, never eat soggy waffles, right? But anyway, so north 42 degrees east. That means that from the north, we're going to go 42 degrees east. So maybe something, I should have used a dotted line, but anyways, maybe something like this, right? That's north 42 degrees east. Okay? South 31 degrees east would look like this. So from the south, you're going to go 31 degrees east. Okay? South 40 degrees west would look like this. Right? You'd be heading from the south, you would go 40 degrees toward the west, right? And north 52 degrees west would look something like this. Okay? So that's how bearings work. If a problem just says, so maybe I'll give you like another example. If a problem just says the bearing of this thing is, you know, 240 degrees, what they're giving you is the angle of rotation from the north, right? So 240 degrees. In fact, I'm going to do it like this. So 240 degrees from the north, So if you go around 240 degrees, this is 90, 180, 270, so 240 is somewhere here, right? Yeah, so it's always from the north, and it's always in the clockwise direction. So it's very much different from the sort of standard way that we think about angles, but nevertheless, if they just tell you that the bearing is 240 degrees, this is what they're talking about. But most of the time, this is the way that bearing is given, which is a little bit more clear in my opinion. Let's just look at an example. So it says, a ship leaves from port and sails on a bearing of north 47 degrees east for 3.5 hours. It then turns and sails on a bearing of south 43 degrees east for 4 hours. If the ship's rate is 22 knots, that's nautical miles per hour, find the distance that the ship is from port. Okay, so let's do this, right? So ship leaves from port and sails on a bearing of north 47 degrees east. So let's say that this is the port right here. And from port, the ship is going to leave on a bearing of north 47 degrees east. So towards the east. So something like this. Okay? So it goes on this bearing. It says it then turns and sails on a bearing of south 43 degrees east for 4 hours. So at this point it turns and it goes on a bearing of south 43 degrees east. So maybe something like this for a certain period of time. Okay. So what you might notice is that what you've got here are some transversal. This bearing right here is a transversal for sure. And this angle was north 47 degrees east. So this was 47 degrees. That means that this is also 47 degrees, in case you're curious. We also know that this bearing here, well, no, which bearing was it? It was, at this point, he turned and went south 43 degrees east, so this bearing here is 43 degrees. Right, that angle right there is 43 degrees. Now, what do you notice about 47 degrees plus 43 degrees? 47 plus 43 is 90 degrees, isn't it? So actually, this angle right here is a 90-degree angle. It's kind of nice, and it might be useful for us because we're asked to find the distance that the ship is from the port. So wherever it ends up, right? And maybe this is like further along. I'm not exactly sure, but we want to find the distance from here to here. Right? This is the distance that we're being asked to find, and we know that this is a 90-degree angle. So this is a right triangle, and the distance that we're being asked to find is the hypotenuse of that right triangle. We could do that pretty easily if we happened to know what the legs are, and guess what? We do, because we know that he was traveling on this bearing for 3.5 hours. So, and we also know that he was traveling at 22 miles per hour. So, so if you go 22 miles per hour for 3.5 hours, then you're going to end up going 22 times 3.5, you're going to end up going 77 miles. So this is 77 miles. Okay, what about this one? He traveled on this path for 4 hours. Oh, so actually probably he's down here somewhere, but whatever, the picture is fine. For 4 hours, still going at a rate of 22 miles per hour. So we'll say 22 miles per hour times 4 hours. Oh, I can do that in my head. That's 88, right? That's 88 miles. So this is 88 miles. Okay, so now I can use Pythagorean theorem. Right, we can say 77 squared plus 88 squared equals hypotenuse squared. (77 squared plus 78 squared is 13,673, and the square root of that number, let's see, how many sig figs do we have? 4.0 hours through, so I think 2 sig figs. So to 2 sig figs, we would say this distance is about, well, see, this is what I got on my calculator, 116.932, but to 2 significant digits, that would be 120, right? 120 miles. So, so the ship is 120 miles from port, okay? Another interesting question that could be asked is, what is the ship's bearing, right? So like, so we know this distance, but you know, what's this angle? That would be an interesting one. But they didn't ask, so we won't try to figure it out. Let's move on. So bearing is one type of problem that you'll see in this section. Another type of problem is this, the subtense bar. So the subtense bar method is a method that surveyors use to determine a small distance d between 2 points P and Q. The subtense bar with length b is centered at Q. Excuse me. It's centered at Q and it's situated perpendicular to the line of sight between P and Q. So angle theta is measured, and then the distance d can be determined. So in other words, if you're trying to figure out the distance between P and Q, then one way that you could do it is to sort of measure this angle where well, so if you know that you have a particular length over here, you're going to center that length at Q, so half of the length is here and half of the length is there. So if you know this length, you can measure this angle, and then given that angle and this length, you can figure out the distance between these 2 points. So this is something that apparently surveyors do. I'm not a surveyor, so so I wouldn't know. But here we go. Let's do some calculations. So part A says find D. In other words, find the distance when the angle is really small, 1 minute 23 degrees 12 seconds. Or sorry, when theta is 1 degree 23 minutes 12 seconds, and when B is 2 centimeters. But look at how many significant digits. We have 1, 2, 3, 4, 5 significant digits. 1, 2, 3, 4, 5 significant digits. So yeah, so let's see if we can do that. How would we do that? So well, if we know that B is 2 centimeters, then B over 2 is 1 centimeter. And notice that this is a right triangle. Furthermore, this angle right here is theta divided by 2, right? Each of these is theta divided by 2, because together that would give you theta. So we have this right triangle where we know this side and we know this angle. We should be able to find D. We could say something like tangent of theta over 2 is B over 2 divided by D, and then solve for D, right? Okay. So let's figure out what theta over 2 is then. So let's see. 23 out of 60. Here's what I'm going to do. So I'm going to say theta is 1 plus 23 out of 60 plus 12 out of 3600, right? Degrees. It's this many degrees. So I want to find theta over 2, so I'm going to divide all of this by 2. And so let's see if I get anything nice. So 1 plus 23 over 60 plus 12 over 3600, all divided by 2. Oh yeah, that's not bad. That's 52 over 75 degrees. Okay, which makes sense, right? That's like less than 1. So it's 0.69 degrees. Right, which makes sense if the entire angle is just a little over 1 degree, then half the angle is, 0.69 degrees or whatever. But I'm going to leave it as a fraction, okay? Now I can say tangent of theta over 2 equals B over 2, right? If B is 2, then B over 2 is 1. That equals 1 over D. And then I can solve for D. Maybe I'll write it out like this. So tangent of theta over 2 is tangent of 52 over 75, right? That equals B over 2 divided by D. So then D is 1 over tangent of 52 75ths. And remember, we're going to round to 5 significant digits. So let's see what we get. 1 over tangent of 52 over 75. So that's about 82.634, right? To 5 significant digits, that would be 82.634 centimeters. Okay, so that's that distance. Okay. So there's that one. Part B says, how much change would there be in the value of d if theta measured 1 minute larger? Goodness gracious. Or not 1 minute, 1 second, right? So if theta were 1 degree, 23 minutes, and 13 seconds, well, let's see. So if theta equals 1 degree, 23 minutes, 13 seconds, then theta over 2 is going to be how much? Well, so that would be 1 plus 23 sixtieths plus 13 3600ths, all divided by 2, which is a pretty nasty number. Theta over 2 would be 4,993 out of 7,200 degrees. Okay, so I'm going to cut to the chase then and say I'm going to use this, but instead of 52/75, I'm going to use this number instead, right? So I'm going to say d equals 1 over tangent of 4,999 7/7200ths, and again going to 5 sig figs, we would get 1 over tangent 4,990. Oh, I'm sorry, it's not 4,999, it's 4,993. I apologize. So this should be 4,993. Anyway, 4,993 divided by 7,200. That comes out to about 82.618 if we go to 5 sig figs. The question is, how much change is there? How much change is there in the distance? Well, so you would subtract this from that, right? So we would do 82.634 minus 82.618, right? And that comes out to 0.016 centimeters. So that's how much change there would be if you measured just 1 second differently, which goes to show you, you've got to be really careful about how accurately you measure. Okay. So there you go. So that's the subtense bar. Here's one more application problem. This one says, Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet. From the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree to the nearest foot. Okay, so let's say that the tree is here, and that from the first location, doesn't say how far it is, so we'll call it X or something, but from that location to the top of the tree is 36.7 degrees. Then it says he moves back 50 feet, and that the new angle of elevation to the top of the tree is 22.2 degrees. Okay, find the height of the tree to the nearest foot. So I'll call the height of the tree h. And I guess we're assuming that the tree stands straight up. Okay, so this distance from here to here is 50, right? And this distance from here to here is x. That means this distance from here all the way to here is x plus 50, right? Okay, now if you know law of sines from some previous trig experience, then this problem is actually pretty easy if you have law of sines. But we haven't talked about law of sines yet, so we're going to have to use kind of a different strategy. And I think what I'm going to do is I'm going to do tangent of 36.7 degrees equals h over x, and then tangent of 22.2 degrees equals h over x plus 50. That'll give me two equations that they both have two unknowns. And so I can solve one of the equations for one of the unknowns and plug it into the other one. So let me show you what I mean. Just starting with the first one, tangent 36.7 degrees equals h over x. And that means that h is equal to x times tangent of 36.7 degrees. Okay? Now, tangent of 22.2 degrees is equal to opposite h over adjacent, which is x plus 50. And that means that h is equal to x plus 50 times tangent of 22.2 degrees. Well, if h equals this expression and h equals this expression, then it should be the case that these two expressions are equal. So therefore, we can say x tangent 36.7 degrees equals x plus 50 tangent of 22.2 degrees. So x tangent 36.7 is x tangent 22.2 plus 50 tangent 22.2. I'm going to move this over there. I'm going to factor out an x. Whoops, x times and then I'm going to divide by all of this stuff to get x by itself. So x is going to be 50 tangent 22.2 degrees divided by tangent 36.7 degrees minus tangent 22.2 degrees. So there's x in all of its nastiness. But anyway, your goal is to find h though. The good news is that now that you have x, well, you can plug it in here to find h, right? Or you could plug it in here, but I think this is a slightly easier formula to use. So I'm going to say h equals x x times tangent of 36.7 degrees. And you can pop all of that into your calculator now and see what you get. How many sig figs? Just one? One sig fig? Maybe we'll count this as 2 sig figs. I'm going to go 2 sig figs. Let's see what we get. So here we go. All right, 50 tangent 22.2 divided by tangent 36.7 minus tangent 22.2 times tangent 36.7. I'm missing a... Where am I missing a parenthesis? So I've got it around the numerator. Oh, there it is. Okay. Alright, let me make sure I got it in there right. 50 tangent 22.2 over tangent 36.7 minus tangent 22.2 times tangent 36. Okay, looks good. So I'm coming up with 45. All of that for 45. But there you go. 45 feet, approximately. So there's the height of the tree. It's about 45 feet tall. Okay, so that's that one, and that'll do it for 2.5.